Okay, thank you. I'd like to thank, this is the inaugural presentation in the New Frontiers DAP project, which was selected, so we're grateful for that support. Yeah, one thing about this community, it seems like, why can't we have nice things, right? And the elephant in the room is the negative buoyancy of cryomagma liquid water is, it's denser than the country rock, which in this case is water ice. We're talking about here density contrast. It doesn't matter what the exact number is, but it's of that magnitude. Something like 80 kilograms per cubic meter. This and people looking at a lot of us come from a basaltic or silicic planet background, silicate planets. Everyone knows that volcanism is smooth and easy on those planets, right? Well, it's not really the case. And Lauren stole a little bit of my thunder, but I guess it's really her thunder because that's what she's been doing for the last 5 years. But so maybe there's a little bit of thunder left that I can use. But for the moon, here's the old state of knowledge. Looking at the density, we've known for a long time there should be some sort of problem there. The country rock is an orthosite. The magmas are dense basalts, and here's a nice plot from Zorik et al. 2001 paper where they're talking about the buoyancy issues, and they plot the liquidus densities of a bunch of different lunar samples, and you can get some pretty honking high ones, especially out in the other parts of the solar system. The basalts come in a bit denser than the ones you see coming out of, like, say, Kilauea, like now. But it's because of the higher iron, titanium, those sorts of things. But in the context of our knowledge in 2001, they were thinking, oh well, here's your density of an orthosite, so you're going to have some buoyancy problems up in there, and then you can get around that. Maybe the crust is layered, and you have a denser lower crust, and that will help you get the magma through. That will help solve that problem. So all is well and good. And then Grail busted that wide open. Grail revealed that taking the theoretical density of a rock like an orthosite is not the thing to do. It's actually, the crust has been pulverized by impacts, myriad impacts over 4 billion years plus of history. So the average crustal bulk density turned out that you could basically, if you have high enough resolution like you did with Grail, you just plot a line on a chart and read it off. The density, bulk density of lunar crust came out to about 2,500 down here. So you have a honking adverse density. You have a much worse problem than you ever did before, and yet somehow the moon is still covered with basalt, at least on the near side. And then we took people like Sander Goossens and his team reanalyzed using sort of the knowledge that we got from how things work with Grail and how to use more advanced processing techniques and insights from Grail. They looked at the gravity data for Mars, which it's been accumulating over the years from the different orbiters that have been there. And they recalculated things to get an average crustal bulk density of Mars, which is much less than, substantially less than what was taken to be the a reality in the years past. And that also gives you, given what we know about from SNC meteorites, the density of basalts from the moon, you're also getting those awful delta rho values, negative buoyancy. How do we deal with that? And yet, Tharsis doesn't care. Tharsis is this giant honking volcanic province with these giant honking volcanoes, and it really is not listening to us complain about buoyancy. So, to take some lessons from these basaltic planets, and you could even do this for the Earth, cases where you've had dense stuff coming up through less dense stuff. But I just in the talk I gave at LPSC, I coined a term BIPS for basin igneous provinces, sort of in the tradition of the LIPS, the large igneous provinces, from books like, this is the Mahoney and Coffin book that came out that talked about all these large igneous provinces of various parts of the Earth. These come in the planetary version, they come in two varieties, intrabasins, what I call IBIPs, and transbasin TBIPs, which I'll tell you about in a second here. So yeah, here's a layout. You see that you have your standard mare filling topographic basins like Serenitas, Crisium, Nectaris. And you also have these more regular things where you have a mare filling in a regular topographic low, which is believed to be a relaxed impact basin. Some of the topography has relaxed over time. And then you have Tranquillitatis, which turns out to be a huge mystery and something that I'm hoping that LDAP will give me some money to look at. There's a big geophysical difference between the eastern part of Tranquillitatis, which is basically got top a crustal plateau, and the western part, which is part of that giant rift system that was mentioned yesterday. So that's an example of a transbasin impact, a transbasin igneous province, and I've been working some of the calculations I've been doing to try to explain maybe the effects of being between the loads of all these three basins may enhance magmatism in Tranquillitatis. So looking at the moon, you start to see that you have the standard in blue, the basin filling mare, and then you also have these zones in red, like Oceanus Procellarum and Tranquillitatis in red, the T-bips, which may have something to do with the stresses from these other basins helping magma to get up. And you have the relaxed basins in gray. On Mars, you have a similar thing where you have the Isidis Utopia basins, which show up very well in topography. In the interest of time, I'm just showing these geologic maps. But then you have these giant volcanic constructs like the Elysium Rise, Syrtis Major, and here's the Hellas Basin with the circumhellas volcanic provinces of different parts off to the northeast and southwest of the Hellas Basin. So these are significant igneous provinces, to say nothing of this giant Borealis Basin, and arguably Tharsis is the biggest T-bip of all for that. So what's the connection? What I've been looking at for quite a few years now is lithospheric loading from the IBIS, from filling of these things with magmatic and sometimes sedimentary materials, create the stress rates favorable to the formation of magma ascent, favorable to the formation of the magmatic systems on the outside. So how can we apply these lessons to cryovolcanism or following Sarah's lead to magmatism at Right Mons Pluto? So these edifices here, Right Mons and Picard Mons, and perhaps some of the things that Caitlin Ahrens was talking about in other places around here, could be these transbasin igneous provinces related to the nitrogen ice-filled Sputnik Planitia up here. So we can calculate scenarios for loading to evaluate how much magma ascent might be encouraged in places that are around the load of the basin through the effect of the stresses on the icy shell icy outer strong shell of Pluto from the loading. So here's a nice figure that Oliver just made, Oliver White, my co-author, talking about perhaps the distance you might get from the center of Sputnik Planitia to Right Mons. I wouldn't necessarily call that the center of what might be the roundish basin. It's a little bit extended because, of course, you have this protrusion down here, which I have an unofficially named Sputnik Bay. It does seem to make the problem more complicated than the initial filling of a roundish basin problem that I would do, but I will just tuck that away there for future reference in terms of how that might be affecting what's going on here, not just from a nice circular load there, but there may have been some ellipticity to the basin, but also there's clearly something a little bit different going on here than in the rest of it. So I'm just going to proceed with a axisymmetric type model for a basin and proceed from there. Yep. Don't use that. That's totally unofficial. So what are the driving forces? I'm getting my math here in terms of how to interpret the stress state from loading from the equations for pressure balance on the outside of a dike, a vertical magma body, from Alan Rubin's annual reviews paper, 1995. Oh God. Okay, well, that's what you get for putting in equations. But here, conveniently, I've described what the equations actually mean, so you don't need all those boxes. So you have the pressure gradient in the magma plus the weight of the magma gives you the a tectonic stress gradient, that should be delta sigma y over delta z, plus the buoyancy term, delta rho g, plus overpressure, delta p, d delta p, that's the magma overpressure from whatever sources, be it volatiles or overheating, whatever you want. So, good thing I put that in, huh? The equation of magma ascent velocity will also probably be mangled because of font issues, but the upshot is you take this term and put this over here and apply the viscosity. There's a viscosity there, and the dike width, and so that equation must be positive to get magma ascent. And with flexure, this d delta sigma, the gradient of the tectonic stress gradient, basically the difference between the horizontal stresses and the vertical stresses, is the dominant term. Okay, all the fonts came in okay on that one. So how this works at fill basins, the large loads are supported by regional scale flexural and planetary scale membrane stresses in lithospheres. So these are, the flexural stresses are sort of a dipole, they're from bending, and the membrane stresses are uniform, they're from stretching. So when you get to these basins that are a significant fraction of the size of the planet, you're going to get a combination of modes here. And it turns out that for flexural stresses, the two stress criteria you want to meet are, is the stress generally extensional? Is it, are the horizontal stresses greater in magnitude with tension positive than the vertical ones? And for flexure, half the lithosphere is good, half the lithosphere is bad. But for membrane stresses, if you're in the right side of it, if you're stretching things apart rather than pushing them together, you're going to get an overall positive thing, which will reduce the size of this negative thing, and you might actually get the gradient here is what's, that's that differential stress gradient is what's basically pumping the magma from down, or from below to above. So there's like a silver lining to this part being in compression. If you're more extensional with height, you're basically squeezing stuff up, and that's the mathematics that helps you get to the place where you actually find that everything's put into extension over here, and you have a stress gradient plus the extension that makes magma want to ascend much more readily out here than it does over here. Eventually, you fill this up, and there may have been, if you look at the hydroco models for impacts, there may be initial extension here that allows you to have magma ascend there, but when you start, starts collecting up there, pushes everything down, shuts everything off, but it may create these enhanced descent zones, or EAZs, to help you get the magma up on the side. So here I'm going to show some COMSOL multiphysics finite element method models where here I have a profile here in spherical axisymmetry. These are all the elements that I'm using in this model are contained in this cross section here. But when you see this, what you should be thinking is this is what it's actually modeling, a 3D situation where I've shown like the stress state, and there's the shell, there's the deformation, highly vertically exaggerated. It's like by a factor of 40 or something just to make it look interesting. But this is what the actual thing, this looks more boring than that, but this is showing that axisymmetry is creating, you're creating a spherical thing, and you're modeling, you're modeling a basin. So there's just an example mesh looking at this close-up in there. You see that the finite elements there, so that's the sort of thing we're doing. And we're putting in the effects of a compensated basin here using basin size parameters from the Keen et al. Paper from 2016. But so this is what happens when you bend everything around a sphere. So if this were a uniform thickness model, and I've done some of those too, the thing would come up a little bit higher there, and it would come up a lot higher there. This is compensated by the density difference between the water and the ice. So this is what would happen in the aftermath and before things have had time to cool and thicken a lot. And you might argue that maybe the load happened after things thickened, and yes, we can model that. But here I've modeled the case where things are happening shortly after the impact. Oh, they're just meters. Yeah, yeah. It's funny because I can, COMSOL gives me extreme abilities to alter. I can select from 20 different kinds of megapascal units on this, from micropascals to megapascals, but I can't change the damn XY axes. It's bizarre. So yeah, we want to show this in picopascals. I could do that, but not really. Yeah, so I made, once you do that, you calculate the load, so you end up putting a load on top of that reflects the stuff that's infilling the basin up to, again, using parameters for thickness that James Kane used in his paper. And you end up getting a prediction for stresses in terms of the principal stress orientations and the differential stress magnitudes, the difference between the greatest and least principal stresses. And what I've done here, I'll just blow this one particular model up. The upshot is that the vertical red arrows, if they're vertical with respect to the local coordinate system, that's very bad for magma ascent. What that means is that your least principal, the least most tensile or least compressive principal stress is vertical. You're not going to propagate anything vertically in terms of a dike. You're actually going to make sills. You're going to make things go sideways. So these sort of areas are very bad for magma ascent. And what's interesting when you get the thin, when you have a thinner plate over here than you do over there, and this is where the load is, the flexure doesn't really come into play anymore. It's all compressive. It's all bad. So that's an interesting wrinkle that doing a more advanced model gives you. And the horizontal red arrows or no red arrows, I'm not sure there are any places where they're actually horizontal, maybe there. those are good for magma ascent. That means you're pulling apart horizontally, and you can have magma come up. And the place, this is there's 3 components to that stress tensor, and where it turns out the out of plane stress, because it's axisymmetric, is the most tensile. Then that's what you don't see the red arrows at all. And it turns out this area where you have the secondary and tertiary principal stresses, the blue and red, and also the tealish part on the color map here. It turns out the teal land is very good for magma ascent. Basically, if there's a fracture here from some pressurization or volatiles or whatever, you're going to be pushing that stuff up. It'll get in, and it will be basically pushed up to the surface by the stress gradient. So that particular area is a thing that you will see in spherical models and you won't see in planar axisymmetric models. So this turns out to be the place where magma ascent is. It's almost magical how much it's favored, but it's pretty outstanding. So at about 7:30 this morning, I finally got a chance to take the stresses I downloaded and turn them into this effective buoyant density calculation, which from the equations where the font didn't come through. The delta rho, that you convert the stress gradient, the difference between the vertical and horizontal stresses, into an effective density offset by dividing by the planetary gravity. And for that one particular model, which I didn't customize in any way, it's the first production model of this whole thing, it turns out that the density offset, depending on position, how far away you are from the center of the load, you can get density offsets that are comparable, but not quite at that magical 80 kilograms per meter cube thing we're doing. But in some places, they actually are greater than that. So you can see we're going a long way to eliminating that buoyancy barrier. And I have no doubt that by changing some of the parameters, like the model properties, but I have a list of them up here, don't I? Yeah, this is right there. So the density offset magnitude would depend on the load parameters, material properties of the spheric thickness, compensation state, and so on. This is literally the first model off the press, and we're already doing quite well. And in places, we're actually exceeding that thing. If you can calculate the velocities from that, you should be able to propagate materials up to the surface very quickly, as required, as Lene was saying, from the thermal aspects of it. Get things up very quickly. You calculate the actual velocities are coming up through there. So this is a way to get to break that buoyancy barrier. So my interpretations, conclusions. So loading of Sputnik Planitia Basin, it leads to an enhanced ascent zone, or EAZ formation around the basin. The stress-based density offset is comparable to the adverse buoyancy of water in terms of the liquid through the solid. The enhanced ascent zone is a necessary but not sufficient condition for the cryomagnetism. You need to have a source from the bottom. That's why when you look at the ones on Mars and the Moon, there's not just an annular zone of magma ascent around there. It depends. You create part of the. You facilitate ascent if there's something there, but there has to be something else there, and you have to provide it by being a warm plume, or maybe there's something in the ductile layer below, which we're not modeling here, that provides that. But it turns out there may be something about the place where Right Mons is that's helping you. It's a combination of things that allow you to get this. So this only gets you halfway. You need that other thing. And the symmetry breaking from what I call the Sputnik Bay implies a role for regional to planetary scale stresses, and we can also do that. Here's a model, for example, where we can break the symmetry, although this is still a quarter sphere symmetry model, but by going up to that scale of a model, it's 3D. So you can model things that have a non-uniform expression across that, such as tidal and de-spinning stresses, which have some degree 2 components, which can be modeled in this sort of model, and also degree 1 and 2 crustal thickness variations. So we can start thinking about why that particular piece of Sputnik Planum is extending down, and you can put that in the models, and then that'll make things probably work even better. So the theory and the models presented here can apply to other cryovolcanism and magmatism candidates, and don't put them in the same categories as Australian table wines. Don't poo-poo cryovolcanism. Thank you.
Cool talk. I have 2 questions. One is about the magic 80 number as the difference between density. So you mentioned porosity on the Moon and Mars. Probably it exists on Pluto too, so maybe the magic number is something like 160, sure. 170 or something.
I said the exact doubling, that does make a difference. I guess it was like 160. But again, that's going to be something And I think Lauren addressed it. That's going to be something that varies with depth, and that's going to be something
Sure.
at the very
Yeah.
top. It's actually that's partially the considerations of why the paper I've written about this about the moon hasn't been published yet, because of resolving issues with various co-authors about what happens at the upper part. Because there's several issues with regard to that, including the porosity density issue you mentioned, and also the way that the stresses go. If you calculate the stresses up to a certain point, it actually hits the yield criteria, and then it'll actually tip the other way. So it turns out that that's where considerations of things like the volatiles end up mattering for that last little step. So that's something we can incorporate in these too. But.
Cool. And speaking of volatiles, my second question is, Terry mentioned in his first talk of the morning polar wander possibly inducing stresses. Do you have a sense of, if you included polar wander of ice loading of Sputnik Planitia, would that help or hurt your case? What would that do to the stress field?
It'll change it. I mean, if you look at James Tolkien's paper, he talks about the different stresses that are involved with moving Sputnik Planitia from a location closer to the pole to closer to the equator and the sub-Sharon point where it is now. I've done some exploration in terms of modeling, like the quarter shell model. I'm modeling things like tidal and working towards modeling things like despinning. I found that the stress magnitudes can matter, and a lot of times those magnitudes are close to the 10 to the 5, 10 to the 6, closer to like 1 megapascal or less, or plus or minus 1, and a half. Whereas the magnitudes of some of these things are in the 3 or 4 or 5, and ultimately working out the balance between those is. Because the other thing about this is that it's modeling the full-on lithostatic stress state throughout the whole thing. So in terms of what's going on at depth, those stresses might not make that much of a difference. In terms of what's going on the surface, they will make a difference. But there's a load of calculation, a lot of work to do to figure out the balance there.
Pat, if we could give you a predicted thermal regime, could you modify your input parameters for a non-constant material parameters?
Well, yeah, there's not much thermal information in this. It's a pretty dirt simple lithospheric structure. COMSOL has the ability to do more advanced problems and solve thermal as well as structural problems, which, when you get into 1, thermophysics, and 2, viscoelasticity, which is, beyond the scope of this, but certainly things that are on our plate. Long term, yeah, that when you start putting those things in, that'll make a difference.
I'm wondering if the general conclusion you're drawing about where the magma is going to go around a big basin, that sort of thing, is that unique to the Pluto or an icy body situation, or is it applicable to large basins like the volcanic fields surrounding Hellas coming around the rim?
That's the origin of the work. That's the work I did. It goes in their direction. That's the work I'm doing. That's my original application of the method.
Okay, and would it predict then that the sources for the Imbrium basalts would be not the bottom of the basin, but the rim of the basin?
Well, if you look at the individual lava flows are hard to see, but the general sense of, I think, of what basins like Imbrium and Serenitatis is that the late stage stuff does come in from the sides, and it actually agrees with my model quite well. But the early stage stuff probably comes straight up, and part of that's due to, if you look at the papers like the Purdue group and Jeff Rangers-Hanna did, there's a crustal annulus that right after the impact, things are sort of in equilibrium, but you tend to get, there's a crustal collar that produces uplift, and that helps magma ascent in the center, but eventually the load reverses sign, and then you push things out to the side.
I'm just wondering, what about cryovolcanism on Europa and places that don't have a lot of topographic relief much at all?
Right, this isn't as useful in terms of the specific
we
application
still see evidence
to a basin.
of it there, but it's, yeah.
Well, that's something, that's where the tidal stresses and perhaps whatever local tectonic effects you have of topography and fracturing end up playing more. So the kind of models I showed don't really help you with Europa very much, but the general technique overall can be used. And once you start getting into more advanced loading and more advanced physics like thermal stresses and stuff, then it has applications in those directions.